When it comes to thinking about redox, there's often too much emphasis on the ox without really thinking about the electrons involved. And well, those electrons are what's really defining redox. So I like the mnemonic oil rig. Oxidation is loss of electrons and reduction is gain of electrons. Now, often, but not always, oxidation is going to correspond to the gain of bonds to oxygen, and the reduction is going to correspond to gain of bonds of hydrogen or loss of bonds to oxygen. And so, yes, it's kind of helpful to think about, okay, oxidation, more bonds to oxygen, reduction, less bonds to oxygen. But thinking of it that way is going to get you into trouble when things aren't quite so simple. And more fundamentally, you're missing the point of redox, which is about those electrons. And especially when we talk about metabolism, when we talk about catabolic pathways, and we think about all these oxidative reactions that are taking place, and these electrons, the electrons are what's getting passed. The electrons are going to get passed to NAD plus to give us NADH, which then we can cash in for ATP in oxidative phosphorylation. And so all of that is going to be taking place because of the transfer of electrons. And so let's step back and think really, what is redox all about? How can we track these electrons? Where are these electrons going? Well, how can we determine whether redox is actually occurring? We can do things like using oxidation numbers, so I'll show you how we can calculate these, as well as show you how this all applies to metabolism. So let's dive in and talk about things. It's a lot easier to use those kind of like simple mnemonics than to think about the electrons, especially when we're thinking about biochemistry, where unlike if you might have learned about redox in like general chemistry, where you're actually seeing whole electrons moving and things like this, in the case of biochemistry, things are a little more hidden. So instead of whole electrons moving, you can think about gain and loss of electron density. And so you want to look at new or change bonds to an atom and see if the electrons are now getting pulled towards or away from it. If you're getting shared electrons pulled away from you, well, now you've been oxidized. And this is often, but not always, going to occur when you form bonds to oxygen because, well, oxygen is really good at pulling those electrons away. When we talk about the ability to pull electrons, we're talking about electronegativity. And oxygen is going to be able to pull those electrons away, and thus the atom is going to have been oxidized. If, however, the shared electrons are getting pulled closer, the atom has been reduced. And well, if you think about when you can pull electrons closer to you, it's well, when if you bind something that's less electronegative to you. And who's the weakest when it comes to electronegativity, who's really, really bad at holding those electrons? The hydrogen. And so if you form a bond to hydrogen, that hydrogen isn't going to be very good at holding onto its electrons, and so you're gaining electron density in that way. Oxidation and reduction go together. If you're pulling electrons from one thing, you're pulling it to one thing. And so the thing that gains electron density or gets reduced had to oxidize something in order to do so. And so we call the first thing the oxidant or the oxidizing agent. The thing that loses electron density, the thing that's getting oxidized, had to reduce that other thing in order to do so. So it's called a reductant or a reducing agent. So how do we determine whether something's a reductant or an oxidant and what the heck is going on? For this, I like to turn to a little dog analogy. So if we think about those atoms as kind of having the protons are going to be held in the central nucleus, and then we have the electrons around it. And I like to think of these electrons as dogs and the valence electrons especially. So the valence electrons you have in your outer shell, and these are the electrons that are kind of going to be the most reactive. These are the ones that are furthest from the pole of the protons in the nucleus. And those protons are kind of like dog walkers that are holding onto them in leashes. The more electronegative the atom is, the kind of tighter those leashes are going to be. This is going to be a combination of how many of those protons they have. So those are the polars, like how much pulling strength they have, as well as how far away those dogs are. So how far out are those valence electrons? And so you have this trend where you go to the upper right corner of the periodic table, and that's where you're going to find the most electronegative things. And so we see that over there, we've got our oxygen, we've got our nitrogen. Sulfur is not too bad. So all these are going to be more electronegative, especially more electronegative than something like our hydrogen. And so what's going to happen is that those electronegative atoms are going to pull more on those those dogs. And so when you're sharing those dogs in a covalent bond, because that's what a covalent bond is, it's dog sharing. Okay, well, what it really is it's the sharing of the electrons. But if we're saying those electrons are dogs, so you can think of two dog walkers walking side by side. One of the dogs starts sniffing the other dog's butt. And now you know it, you have these two walking side by side. And well, who does the dog like more? Does it like the first owner or the second owner? And therefore, you can kind of determine, do we get a shift in our loyalty of the dogs, in which case we would have one of the molecules being reduced and one being oxidized, or do we not have any change at all? If you have a fully covalent bond, well, here you're going to have fair sharing between them. You can think of both of the protons being kind of like equally good at wooing the dogs. And so those electrons are shared fairly. If you were to split them up, each owner would still have a dog. But now imagine that you have a situation that is not so fair. Like maybe you have that oxygen, which we said was really electronegative, and it's bonded to a hydrogen, which we said was like really, really not electronegative, electropositive. And so what's going to happen is that the dogs are going to, if you were to split these up, the dogs are going to stay with that oxygen. They've changed their loyalty. And therefore, if we were to compare the state of this hydrogen and the state of the oxygen before and after, well, if we think about in a fully covalent bond, if we have this fair sharing, well, here each of these hydrogens owners was going to have an electron, and yet here it doesn't. And so what would have happened was that, well, going from that pure hydrogen to the water, the hydrogen is going to have lost electrons. And when we say losing electrons, we say it's oxidation. But the oxygen, well, if you compare just like pure oxygen, O2, you would have fair sharing between those because that would going to be one of those fully covalent bonds. However, now you get two electrons, you've got one from each of those hydrogens. Voila, you've gained electrons, you've been reduced. Do not confuse hydrogen with a proton. Protonation and deprotonation are not redox. By definition, a proton has no electrons. Redox, remember, is all about the electrons. If we don't have any electrons, we're not doing redox. So remember, we said that if we split these dogs up, we would still have the electrons stay with the oxygen. So it's like the oxygen already won those electrons. And so now if we're saying that the hydrogen is just leaving, that's what we said was theoretically happening before, was hypothetically happening before. And now we're saying, okay, let's actually go and actually do it. That's not going to change things. You already had that reduction happen and that oxidation happen before you lost that proton. Losing the proton is not changing anything in terms of your oxidation or your reduction. So protonation and deprotonation are not redox reactions. So in the case of deprotonation, we have the dog walker leaving without the dog. In oxidation, a dog and not just the walker leaves, or the walker gets swapped with a dog that's harder to woo. So for example, if you went from having that oxygen bound to hydrogen, which it could kind of take nicely, to having a bond to another oxygen where now it has to share fairly, that would be an oxidation. And similarly, if we went from having this pure oxygen where it was sharing fairly, and then when it split, it would only get one from the bond, to having a bond to a hydrogen, well, now it would be basically gaining the electrons from the hydrogen. It would be being reduced. And we think about those were kind of like hypothetical situations. But in the case of an ionic bond, well, here what's actually happening is you are getting that whole that split actually changing. So we could think about the hypothetical changes as being what would happen if those bonds were ionic. And this is going to help us think about something more formal called an oxidation number. The oxidation number is saying, if you were to go and actually split those up, so do those hypothetical splits, who would get to keep the custody of the electrons, and what would the owner's charge be? How do we determine who gets to keep them? Well, we have to go based off of electronegativity. And so remember, we have hydrogen, which is our weakling, and we have oxygen, which is our really electronegative one. In between, we've got, so we go from hydrogen to carbon to sulfur to nitrogen to oxygen. What we do to determine the oxidation number, I will show you a couple different strategies. The first strategy is to take the valence electron, the number of valence electrons in the neutral form, And so remember, for that, we just look to our periodic table. Thankfully, with biochemistry, we're typically dealing with a small number of elements. And so we've got our hydrogen, which had 1. We've got our carbon, which has 4, our nitrogen, which has 5, and our oxygen and our sulfur, which have 6. And we also have our phosphorus, which has 5. So we're dealing with these few ones. We can handle it. What we do to find the oxidation number is now we need to take the valence number in the neutral form. So remember, that's just going to be from the column of the periodic table. Subtract how many it would own if the bond were ionic, and voila, we've got our oxidation number. So you take that valence electron number from the neutral form, so just that column of the periodic table. You subtract how many it would own in the split. Remember, that more electronegative atom is going to get all of them. And then you get your oxidation number. And the sum of the oxidation numbers for an atom, for all the atoms in a molecule, should equal the formal charge of that molecule. That's a good way to check whether you did things right. How do you determine how many electrons you would own from a split? Well, think about how many electrons are in a bond. If you have a single bond, that's going to be 2 electrons. You got a double bond, now you got 4 electrons. Triple, you're up to 6. If it's fully nonpolar, so remember our nonpolar situation, they were sharing fairly, so that would be worth half of the bond value. So instead of 2, you get 1 for a single bond, you get 2 for a double bond, and you get 3 for a triple bond. But really, it's not like you're getting anything because those are ones that you had before. And so this will get us to a second type of strategy that I'll show you later, where we can kind of think about each of the interactions and whether it's gaining or losing, comparing to what it was before. But in this strategy, this first strategy, you're just taking how many it would have if you were to split all of those up. Subtract that number from the number of valence electrons, and you will get your oxidation number. So if we go back to our examples, we have our fully covalent bonds. Remember, here we have pair sharing. The neutral form of hydrogen, well, that had 1 electron. We split them up. It still has 1 electron, so 1 minus 1, voila, we have 0. And in fact, an atom, a molecule in its atomic form is always going to have an oxidation number of 0. But what about our situation with the polar covalent bonds? We've got unfair sharing here. If we said that the oxygen was going to win them, so we split them up, we take that oxygen, which before it had 6 valence electrons. Now we're saying we get 8 valence electrons. And voila, we get 6 minus 8 is minus 2. What about the hydrogen? Well, the hydrogen, it before had 1 valence electron, and now it has 0. So 1 minus 0 is plus 1. And we've got 2 of those hydrogens, so we have 1 plus 1. Minus 2 is 0. So overall, the oxidation number of this molecule is 0, which is good because that's what the charge of the molecule is. So remember that check where basically the sum of the oxidation numbers for all the atoms in a molecule should equal your formal charge. So that was a polar covalent bond. Now let's look back at our example with our deprotonation. In this water form, well, we were just looking at, we said that the oxygen was going to have an oxidation number of minus 2. Now let's now go and see what the oxidation number of that oxygen would be if we were to deprotonate it. We've got 6 electrons in that neutral form. Now we have 8 electrons. 6 minus 8 is minus 2. Nothing has changed. Similarly, the hydrogen, we said that, well, if we were to hypothetically split them, the hydrogen would have no electrons, whereas it had 1 in its neutral form. Well, now we've got 1 minus 0 is plus 1. If we think about over here, the hydrogen, if it actually leaves, the proton, if it actually leaves, you still got a plus 1 because you don't have any electrons, whereas you had 1 in your neutral form. 1 minus 0 is 1. The sum of our oxidation numbers is going to equal the formal charge. Protonation and deprotonation are not redox. In the atomic form, the oxidation is always going to be 0. If you gain a bond to a more electronegative atom, that is going to be kind of you're losing 2 electrons. And if you gain a bond to a less electronegative atom, you're going to be gaining 2 electrons. So if you gain a bond to a more electronegative atom, that's a plus 2 change. Gain a bond to a less electronegative atom, that's a minus 2 change. So we were looking at this first strategy. You subtract the number of valence electrons owned if ionic versus the number of valence electrons the atom has in its neutral state, and you determine the oxidation number in that way. Sometimes I think it's easier to do the second strategy. Here you start with the charge of the atom and then consider each bond the atom is involved with. And so when we talk about bonds in this case, like a double bond would count as 2. Then what you're going to do is take them bond by bond. If the atom wins the electron tug of war, so if it's more electronegative, subtract 1 from the charge. If the atom loses the electron tug of war, that is, it's less electronegative, add 1 from the charge. If the electron tug of war is a draw, so it's a bond between the same atom, then there's not going to be a difference. So now let's look at some examples where I'll show you how we can use each of these strategies. Going back to the first strategy, I want to introduce another analogy. In this case, poker chips. I like to think about things like poker chips because, well, when we think about the breakdown of molecules, these oxidative reactions, we're thinking about kind of potential money. So things that we could chip in later for energy. And so we can pass off electrons that we can then take through to the electron transport chain to make ATP. And so I like to think about kind of the number of electrons as being how much fuel you have. In this example, we have formic acid. And if we think about this central carbon and its neutral form would have 4 electrons because it's got 4 protons. We're going to take them split by split. The carbon is going to lose to both of those oxygens, but it's going to win from the hydrogens. And the oxygen is going to win from everything. So we say carbon, it's got 4 protons, 4 minus 2, which it now has. Now we're going to have a +2 charge. The oxygen, well, it had 6. Now it's going to pick up another 2 from this carbon, so it's got 8 total. 6 minus 8 is going to be -2. If we think about this oxygen, well, here it's getting 1 extra from the carbon and 1 extra from this hydrogen. So 6 minus 8 is -2. And if we think about this hydrogen, it had 1, now it would have 0, so a +1. If we think about this hydrogen, same thing. 1 minus 0 is a +1. So in this strategy, we're kind of counting how many it currently has versus how many it would have in its neutral atomic form. However, you kind of might have realized that I was kind of taking a shortcut when I was determining how many it would have. Because I said, okay, well, the carbon it's gonna get this 1 from the hydrogen, and it's gonna lose 1 to this oxygen. And if we think about this one, well, here it was actually going to lose 2, 1 per bond. We had our carbon, we gained 1. So remember, a gain of electron is a -1. We lost an electron, so that would be a +1. We lost another electron, another +1, and another electron, another +1. So if I look at this carbon, I say that it's going to gain 1 and lose 1, 2, 3. And therefore, we're going to have 3 minus 1 is +2. If we think about this oxygen, now it's going to be basically gaining 2 electrons from this carbon. So that'd be a -2. We think about this oxygen, well, it's going to be gaining an electron from this carbon and an electron from this hydrogen. So we get -1, -1, -2. For the hydrogen, we are going to basically be losing our electron to the carbon. And so if we're losing an electron, that's going to be a +1. So you might realize that apart from the molecular hydrogen, the oxidation number of hydrogen is always going to be +1 because it's basically always going to lose that tug of war. For oxygen, well, it almost always wins. And so you're always going to have that oxygen have a -2. And then remember that if they just have a protonation or deprotonation, then you're not going to have any change in the oxidation number. And so if we look at a molecule and we look at its oxidation number, we can tell whether redox has occurred. But if we want to think about things that way, well, now we need to think about how do we actually determine those oxidation numbers. So let's look at some fuels, and we're going to focus on the carbon because, well, like we just saw, oxygen is almost always going to have a -2. Hydrogen is almost always going to have a +1. Those are really boring, and I don't want to just go through all those like over and over and over again. So let's focus on the carbon. So here is an example of going through some of these oxidation numbers. If we think about methane, this is going to be our most reduced form of carbon. And if we think about carbon dioxide, that's going to be our most oxidized form of carbon. Knowing what we know about oxidation numbers, we would therefore expect that in carbon dioxide, the carbon is going to have the highest oxidation number, as opposed to in our methane, where it would have the lowest oxidation number. And this corresponds to having the most bonds to hydrogen versus having the most bonds to oxygen. Because oxygen is going to be very polarly away, it's going to take all the electrons that carbon has to offer. Whereas with hydrogen, now carbon can take those electrons from the hydrogen. So let's go through and look at how we can calculate this with both of our oxidation number strategies. With the first strategy, if we consider carbon, remember we have 4 valence electrons. If we think about how many it would have in the split, it's going to win all of these splits with hydrogen. So now it would end up with that full octet. It would have its 8 electrons. So if we said we had 4, now we have 8. 4 minus 8 is minus 4. What about methanol? Here we are switching one of those bonds to a hydrogen. Now we're bonded to an oxygen. So now the oxygen would win those. And so what we'd be left with is our 4 minus 6. So that would be 4 minus 6 is minus 2. Formaldehyde, now we're saying, okay, we're going to form another bond to oxygen as opposed to just having that bond, a bond to hydrogen. Now what we're going to do is we're going to only be left with 4. Well, we had 4 in our valence form. 4 minus 4 is 0. Here, you're saying, okay, well, now let's take away one of those other hydrogens and bond to another oxygen. And so now we'll be left with 2. 4 minus 2 is plus 2. Finally, we move that last hydrogen. So we go from being able to take a hydrogen from electron from hydrogen to having to give an electron to our oxygen. So we go from having 2 to having 0, and 4 minus 0 is plus 4. One of the reasons I like strategy 2 is that you kind of don't have to think about even separating things. You just have to look at them bond by bond. In this case, we say that in each of these bonds, the carbon is going to be gaining 1 electron from the hydrogen because the carbon's more electronegative. So we say 1, 2, 3, 4. We're going to gain 4 electrons, and each of those electrons has a minus 1 charge, so that would be minus 4. In the case of our methanol, here we get 1, 2, 3 electrons, but in the case of our oxygen, here we're losing one of the electrons. And so what we're going to say is we get minus 3 plus 1. Minus 3 plus 1 is minus 2. In our methanol, our carbon is going to now, it's only going to be gaining 2, and it's going to be losing 2. 1 for each of these bonds. 2 minus 2, we get 0. Formaldehyde, now we're going to gain 1, so our minus 1, but we're going to lose 3. 1, 2, 3. Minus 1 plus 3 equals plus 2. And finally, our carbon dioxide. Here, we're going to lose 1, 2, 3, 4 electrons, 1 per each of those bonds to oxygen. And therefore, we're going to have a plus 4. One thing to note is because that carbon wasn't charged, I started with 0. However, if the atom is charged, then you have to start with the actual charge. This comes into play with things like nitrogen. With a thing like a nitrogen, if we consider the oxidation number of the nitrogen in cysteine, say, in its protonated form, there are a couple ways that we could go about this. We could say, okay, well, nitrogen, it has 5 valence electrons. If these were to split, it would keep both electrons from each bond to hydrogen and from the bond to carbon. So 4 bonds with 2 electrons each, it would have 8. 5 minus 8 is going to be minus 3. If we think about these bond by bond, we say that each of those, it would be gaining 1 electron, which would be minus 4. But we need to consider that it had a plus 1 before. So plus 1 minus 4 minus 3, you get the same answer with each of these. So just remember that you have to start with the charge. And so if it's neutral, then your charge is 0 and you're starting from 0. But if you do have a charge, you do need to take that into account. Speaking of charge, remember protonation and deprotonation? All that's changing is the charge. All you're losing is a proton, not the electrons with the hydrogen. So if we go from, say, formic acid to formate, here in this case, all we have is the deprotonation going on. if we're saying we are actually going to split these, that's not different than saying, what if we split these? In the terms of our oxidation number is not going to change. So in this case, we're actually going to look at this oxygen. So remember, oxygen would have this -2 state because it's going to be gaining an electron from this carbon and gaining an electron from the hydrogen. So we can think about 6 minus 8 is going to be -2. Or we could think about, well, it gains 1 and it gains 1, and it started with a charge of 0, and so it's going to be a -2. Whatever way works for you, know this oxygen is a -2. Now we say, let's go and take that proton away. If we take that proton away, well, the oxygen had already stolen its electrons in the hypothetical state. So if we actually make it happen, it's not going to change the oxidation number. The oxidation number of oxygen is still going to be -2. And that proton is still going to have that +1, just like it had before, because it had pretty much already lost that electron because the oxygen is so much better at pulling it. So when we have protonation or deprotonation, that is not going to be redox. The only reason we typically have these changes in bonds to hydrogen and oxygen be corresponding to redox is that if we think about, well, if you're going from a bond to hydrogen, that's going to be free electrons. If you then are bonding to something else, like something like an oxygen, well, now you got to give away those electrons. And so because the oxygen is so much pullier, and we say that oxidation is loss of electrons, well, you're losing the electrons because the oxygen's taking them from you. Whereas before, you could have gotten electrons from the hydrogen, you could have been reduced by the hydrogen. You might also realize that we're typically moving by numbers of multiples of 2. So we're going from -4 to -2 to 0 to +2 to +4 when we think about the carbon's oxidation state. And one of the reasons why this is that we are basically losing 2 electrons in each of these changes. Let's think about going from methanol to formaldehyde. We had to remove this proton. So we lost a proton, and then those electrons could kind of shift down here to form this double bond. But we would have too many bonds to this carbon. And so we have to actually remove this hydrogen with its electrons. If we think about a hydrogen with its electrons, that's what we call a hydride. So we need to lose this hydride and a proton to go through each of these. And because we're losing 2 electrons, well, now our oxidation number is going to increase by 2. Where are these electrons going? These electrons are often in biochemistry, these electrons are going to be going to NAD+. And this is going to leave you with NADH. So we get this transfer of the hydride to the NAD+. The NAD+, the plus refers to the charge on the nitrogen, not to the charge on the NAD+. If we think about NAD+, well, overall, it's still going to be negatively charged, but this nitrogen is positively charged. And the reason why we emphasize this is this makes the nitrogen really want electrons. And so it's going to serve as a sort of electron sink. In this ring of the NAD+, what you have happen is the hydride is going to add on to this. This pushes the electrons around the ring onto the nitrogen, and this makes the nitrogen happy because you're giving a positive thing negativity. That's going to neutralize that, make that all happy. Voila, you've got your hydride transfer. And then remember, too, that we had that proton that we had to lose. You can think about things a couple different ways. If you think about the electrons from this oxygen flowing down to form a double bond, now what's happened, and you kick off the hydride, you would have a positive charge here in which your base could remove, because that would not be very happy. You can also think about the base removing the hydrogen beforehand, then the electrons flow down, and voila. In either case, once the base is protonated, well, either the base could be water, or it could basically then lose the proton to water. Free solution. Anyway, that's how you get that kind of plus, that proton. If you think about going from a carbonyl to a carboxylic acid, well, here we can think about, okay, well, if this hydride were to leave, we would have a positively charged carbon. That wouldn't be happy. So a water could attack it, and then you would get this OH and a proton. Voila. Let's think about how this happens in our malate dehydrogenase. So remember malate dehydrogenase, it takes malate and it takes electrons from malate, puts them onto NAD+, leaves you with oxaloacetate and NADH. And of course, it can go the other way as well. How does it actually do this? Well, we can see that what's going to happen is you have the cysteine in the active site with this nitrogen that is just poised and ready to take a proton from this malate from the alcohol group of the malate. When it does this, it allows for the hydride to be transferred to the NAD+. The electrons are going to flow around the ring to the nitrogen. That plus charged nitrogen is now not going to be plus charged. It's going to be happier. And voila, you're left with NADH, as well as with, now you have oxaloacetate. But you have the cysteine be protonated, which wouldn't allow the reaction to go anymore. So you have to have a water or something come and deprotonate that. And then that's how you get that proton released. It's not just in the malate dehydrogenase reaction where you have pass-offs of electrons to NAD+. You see it all over the place in metabolism, including in glycolysis. So glycolysis uses up NAD+, and it generates NADH. In order to keep glycolysis going, you're going to have NAD+ available. Not only do you need it for the reaction to happen, but NADH is going to inhibit some of the enzymes that are needed for catabolism. And so your body has ways in which to regenerate that NAD+. Either you can use anaerobic fermentation to make like lactic acid if it doesn't have the oxygen, but if it has oxygen, it can go through, and it has the electron transport chain available to it. It can go through that, and then it can regenerate the NAD+ that way. So you need that high NAD+ to NADH ratio for glycolysis to happen. NAD+ is good because having a bunch of it is going to make your reaction more thermodynamically favorable. If we think about thermodynamics and free energy, remember the favorability is going to depend on the ratio of products to reactants, because we want our products to reactants ratio to be low so that we have more reactants and are driving towards products. If we say that our products here would be NADH and our reactant would be NAD+, we would want this number to be very small. So we would want to have a little bit of products and a lot of reactants, which would mean having a low ratio of NADH to NAD+, and that'll help make our reaction more favorable. However, what's not so good is then if you want to actually go and reduce things. And so if you want to reduce things, you want to have a different stockpile. And so this different stockpile that we often use is NADPH. It's got that same ring and all that great stuff that NADH had and that NAD had, but we can kind of flip the ratio around and keep a lot of the NADPH form, the reduced form, as opposed to the oxidized form. And if we have a bunch of the reduced form, now we can use it to reduce other things. One of the other things that we use it to reduce is a molecule called glutathione, which is a cellular-like antioxidant. And so now let's talk a little bit more about glutathione and when our bodies use it. This goes back to one of the reasons why I think it's important to think about the electrons and actually calculate oxidation numbers and stuff, rather than just focusing on the simple rule that bound to an oxygen is typically going to be an oxidation reaction. But of course, the first thing I'm going to show you is that a bond to an oxygen is going to be an oxidation reaction. In proteins, one of the oxidation reactions that often occurs is going to be the oxidation of cysteine. Why does this occur? Well, because that sulfur can get oxidized, especially if there's like reactive oxygen species around. If we take sulfur, well, sulfur, it's right below oxygen on the periodic table. It's going to have 6 valence electrons. But because it's lower down, it's going to have a lower electronegativity than that oxygen. If we want to calculate the oxidation status of our sulfur, we can think, okay, well, if the sulfur, we're assuming it's going to be bound to a carbon. It's more electronegative than carbon, so it wins that one. It's more electronegative than hydrogen, so it wins that one. There's no charge on this, so you would have a -2 oxidation state. You could also think about, okay, well, it's got 6 valence electrons. If we were to split these up, it would now have 8. 6 minus 8 is -2. We'd have an oxidation state of -2. Now, however, if we form a bond to an oxygen instead of that bond to a hydrogen, this is what we call sulfenic acid. We're going to be losing that to the oxygen, but we still get the one from the carbon. So they balance out. We've got a 0 oxidation state. If now, however, we oxidize things further, we get sulfonic acid. In this case, we have 1, 2, 3 bonds to an oxygen. And so in each of those bonds, we're going to be losing an electron. So that would be a +3, but we still get this one from this carbon. And so that would be 3 minus 1 is going to be 2. And finally, if we think about over here, our sulfonic acid, well, here we have 1, 2, 3, 4, 5 that we're losing to the oxygen. So that would be +5. But we still had this one to the carbon. So that would be a -1. So 5 minus 1 is +4. Voila, oxidation is happening. Oxidation numbers are increasing. And if we go the other direction, reduction would be happening and our oxidation number would be decreasing. That was bonds to oxygen, but it turns out that sulfur is also electronegative, and it's more electronegative than carbon. It's more electronegative than hydrogen. And so it's not as electronegative as oxygen, but if you swap out a bond to a hydrogen to a bond to another cysteine, well, now what's going to be happening is that is going to be oxidation. You go from getting those electrons from the hydrogen to having to share fairly with the other sulfur. And so what's going to happen is now you're going to have had an oxidative reaction occur. So cysteines can form these sort of like crosslinks within a protein or between proteins, and this can be controlled for making protein, like sturdifying proteins, or it can be uncontrolled when you have like reactive oxygen species happening. When you form these crosslinks, so these disulfide bridges, they're sometimes called, that is going to actually change what we call the cysteine. So we go from having like cysteine to having cysteine. And so basically you lose the electrons and you lose the E in the name is how I remember it. And so that would be oxidation when you are going and forming these crosslinks, because you're taking that bond to hydrogen where you got to take the electrons to a bond to a sulfur where now you have to share electrons. So that's going to be an oxidation reaction. Kind of like we saw when we had our OH versus we had the O2. When you're sharing fairly, you're getting basically losing electrons compared to if you got electrons from the hydrogen. However, we can also think about with cysteine, if we were to go from a thiol, so the protonated state, to the thiolate, the deprotonated state, this is not going to be a redox reaction because, as we said before, that proton was already basically giving up its electrons to the sulfur in the hypothetical scenario. And so now we say if that actually happens, then the sulfur is not going to be changing its oxidation number. If you want to actually think about the oxidation number, well, here we're going to be gaining 1 from the carbon, 1 from the hydrogen. We're gaining 2 electrons, -2. Here, we have to think about, okay, well, we're in a charge state. And if we start with our charge state, well, now we start at a -1, and then we have another -1 from this carbon. -1 minus 1 is -2. Or we could go with strategy number 1. This sulfur, it has 6 valence electrons. If we were to split these up, it would keep all of them. It would have 8. 6 minus 8 is -2. Here, if we were to split this from the carbon, we'll have to think about one split. It would win those. 6 minus 8 is -2. No redox occurring when you have protonation and deprotonation. But yes, redox occurring when you have this crosslink formation. If you think about the sulfur, that was at -2. Now you think about it now. Well, here, it would have to share this fairly. And so here, we would get none from this bond. And we would still get this one, so that would be a -1. Same with this sulfur. And if we think about the other strategy number 1, if we were to split these up, the sulfur would only get to keep 1 from this bond, but it would keep 2 from this bond. And then it would have had these 2 lone pairs. So you go from having 6 to having 7. And so you're going to have a -1. So each of those has increased by 1. And so we can still get that net change of +2. How do we undo these crosslinks? In our bodies, we use a molecule called glutathione. And glutathione is kind of made up of amino acids, and it serves as a source of reducting power. It's like our antioxidant that our cell uses the most. It's able to reduce these crosslinks by forming sort of like mixed disulfides in the process. So this is actually showing you how this happens with DTT. So DTT is a commonly used agent in the lab to reduce crosslinks. We want to reduce these crosslinks because they do things like mess up our protein gels. If you get those like weird reactive oxygen species modifying the protein or causing crosslinks between different parts of the protein that you don't want. Also, some multimers are held together by disulfide bonds. Not all of them, but some of them. And those ones that are held together by disulfide bonds wouldn't be able to be separated if with just heat and SDS. So instead, you have to also add the reducing reagent. And so that's why we added the beta mercaptoethanol to the loading buffer for our SDS page gel. Speaking of having disulfide bonds in proteins, typically you're going to find them in proteins that are secreted because it's going to allow the proteins to be like sturdier. But because we try to prevent unwanted crosslinks inside of cells, it's going to be a reducing environment inside of our cells, and so that you wouldn't have just like nilly-willy crosslinks forming. And the crosslinks you do want to form, you actually go through special processing pathways inside of the cells to kind of protect them from that reducing environment until they can get where they need to be. And so glutathione, really great. But glutathione, in order to reduce those crosslinks, it becomes oxidized in the process. And when the glutathione is oxidized, it's no longer useful for reducing things. If you want to use the glutathione again, you need to reduce it. So how are we going to reduce it? Well, remember we said in our bodies, we typically use NAD plus to oxidize things, but we wouldn't want to use NADH to reduce things because we purposely keep a really low concentration of NADH. Instead, we want to turn to something different. We want to turn to our NADPH. Our NADPH is really good because we can keep a high concentration of it. We can regulate it separately from the NAD+. It still has that same reactive part that's good for these redox reactions. But here you've got a difference. You've got this extra phosphate group, which means that enzymes can kind of like tell it apart, and you can regulate them separately. We can keep this high proportion of NADPH as opposed to NAD+. And now we have this stock of antioxidant in our power to reduce this, that glutathione to regenerate the antioxidant NADPH. And then we can use this to combat those changes that happen to those cysteines and things because of reactive oxygen species. Or we can kind of take the hit before those other things, before things get too bad. And so voila, NADPH, great. NADPH is also really useful for anabolism. So if we said that catabolism was the breakdown of molecules and it was often oxidative, well, anabolism is the reverse. It's the making of molecules, and it's often going to be reductive. And so we see NADPH be used in the synthesis of lipids. So our bodies use NADPH and glutathione to help reduce things. At the salon, you might use a molecule called ammonium thioglycolate. Cysteine crosslinks hold together proteins in your strands of hair. So the protein keratin is really abundant in your hair, and it's got a lot of cysteines. Those cysteines form crosslinks, and depending on how they form those crosslinks, you might get really curly hair. If you use this reducing agent, you break up those crosslinks, and then you can add an oxidizing agent like hydrogen peroxide. Once you've kind of put the hair in the shape that you want it in, that's going to allow these new bonds to form that hold in place this new shape, as opposed to the old shape that you didn't want. So if you were to break those bonds, then curl your hair up around curlers, then add this oxidizing agent, well, now those crosslinks are going to form, but they're going to form in the form that's going to hold together that new style. All of that has to do with redox. So oxidation, loss of electrons or electron density, reduction, gain of electrons or electron density. We can make things formal by calculating the oxidation number. There are two main methods to do this. The first is you subtract the number of valence electrons owned if it were ionic from the number of valence electrons the atom has in its neutral state. So that's just the column or group of the periodic table. And that'll give you the oxidation number. Alternatively, start with the charge of the atom and then consider each bond it's involved with. If the atom wins the electron tug of war, that is, it's more electronegative, subtract 1 from the charge. If the atom loses the electron tug of war, that is, it's less electronegative, you gain 1 in your charge. If it's a draw, so you've got a bond between the same atom, no change in number. You also don't get a change in number with a protonation or deprotonation. That is not redox. But if you compare two molecules and you increase the oxidation number, that means it's been oxidized. A decrease in the oxidation number means it's been reduced. And the sum of the oxidation number should always equal the formal charge. If we're comparing molecules, we typically see things move in chunks of two, because if you gain a bond to a more electronegative atom, that's going to be a +2. A gain to a bond to a less electronegative atom, that's going to be a -2. If you have an atomic form, the oxidation number is going to be 0. The oxidation number of hydrogen is almost always going to be +1. The oxidation number of oxygen is almost always going to be -2. And if all that's changed between two molecules is protonation state, the oxidation number is the same for both of them because, by definition, a proton has no electrons to give or take. But fuels, like our biological fuels, do have electrons to give and take. And so we see these oxidative reactions be used where we're passing those electrons from these different molecules in a series of oxidative reactions onto NAD+. When we do that, we generate NADH. The key place that you see this happening is in the citric acid cycle. We're generating a lot of NADH. That NADH can then be used in the electron transport chain to give you ATP. Voila. Redox.